For each of the derivatives given below, state what would be the original function. In other words, we're finding antiderivatives, right? If my derivative is 2x, what was the original function? Yeah, that would be x squared. Kyle, if my derivative is 3x squared, what would have been my original function?
X cubed.
X cubed. If, Gwyn, my derivative is 4x cubed, what would have been my original function? X to the fourth. Kyle, if my derivative is x cubed, what would have been my original function?
X to the fourth over 4.
Yeah, perfect. Gwyn, if my derivative is x squared, what would have been my original function? Very good. Kyle, if my derivative is x, what would have been my original function?
Oh, 2x squared.
You're close.
One over 2x squared.
Perfect. 1/2 x squared. Gwyn, if my derivative is the number 5, what would have been my original function? 5x. Kyle, if my derivative is 0, what could have been my original function?
Would have just been a constant?
Yeah. Any old constant has derivative 0, right? And so for that purpose, we could honestly go back through here and say, well, my original function could be x squared plus a constant, because in the derivative, the constant goes to 0. The derivative of a constant is 0, so that x squared plus a constant would still have derivative 2x. And I can do that for every single one of these. For example, the derivative of x to the fourth plus a constant would be 4x cubed. And the general answer, I mean, while what we wrote down is correct, but we could have also just written down plus any constant, and it's still true, right? So to give a more generic answer that encompasses the set of all possible antiderivatives, we should really be adding a constant to each of these. But in any case, moving on. If my derivative is x to the negative 3 power, what would have been the original function? Yeah. So when I take the derivative, I bring down the negative 2, and then, yeah, all that cancels. Yeah, and plus the constant if I want to. If my derivative is x to the negative 2 power, what would have been the original function, Kyle?
Negative x to the negative 1 power.
Very good. If my original function is x to the negative 1 power, what would have been the original function? Mm-hmm. Yeah. You guys are too smart. I love asking this question in Calculus 1 because students will normally say something like x to the 0 power, right? Because they're getting in the pattern of just raising the exponent by 1. But you're right. This is 1 over x, and the antiderivative of 1 over x is the natural log of x plus a constant. Okay, the antiderivative of a function is another function whose derivative is whatever function we're talking about. We use a tall curly symbol to designate the antiderivative. Kyle, tell me, what's the antiderivative of cosine of x? Sine of x. Gwen, what's the antiderivative of sine of x? Negative cosine, very good. And again, I should be writing plus c at the end for all of these. It's an important enough thing as a concept that I might take off like 1 point on a test question if you don't put the plus c at the end. That might sound a little bit silly, but for example, in differential equations, I'm teaching differential equations this semester, and that plus c is incredibly important when you're solving differential equations. It really does matter. So we'll try to remember the plus c every time we can. What's the antiderivative of secant squared? Tangent. And what's the antiderivative of e to the x? Just e to the x. Very good. So I'm not going to spend too much time on this because I think every professor explains this in Calculus 1, so I think you guys have seen this before. But when we talk about an integral, the definition, the formal definition of what an integral is this limit. It's the limit of a Riemann sum when I let the number of rectangles in the Riemann sum approach infinity. And I'll open this up in Desmos. You can see what it looks like. That's not supposed to be it. Okay, sorry. I got one of my DiffyQ links confused with one of my calculus links. So like this is a Riemann sum, right? If I have a blue curve here, that function, and I want to approximate the area underneath the curve, I could do so by making little rectangles that fill up the space, the interval. They all have equal width, and the height of the rectangle is given by the value of the function at the left side of the rectangle. And when I add those up, it gives me an approximation of what that area should be. And the way that we define an integral in calculus is we say, let's take the limit as n approaches infinity, meaning let's take the limit as I subdivide this interval into more and more and more and more and more and more little tiny rectangles, and it gets better and better as an approximation of this area because those little gaps get smaller and smaller, and by the time we have a whole bunch of rectangles, like 100 rectangles, it's getting to be pretty good. And the approximation only gets better and better as n approaches infinity. So in this way, in this way, an integral is kind of like the area under a curve. So you could say, why do I care about calculating integrals? Well, in geometry, an integral would allow you to calculate the area in between the curve and the x-axis. Where the lower and upper bound of the integral tell you where to start and stop on your horizontal axis real number line here. Some other examples. If you want to know the total distance traveled by an object and you happen to know a function describing its velocity at any time, then the integral gives you the total distance traveled. If you knew a function describing the flow rate of water, then an integral of that function could tell you the total volume of water. If you happen to know a function that was describing an electric current at any given time, then an integral of that function could tell you a total electric charge that's been accumulated. And this is just 4 examples, but honestly, there's thousands of other applications, right? We're going to talk about a lot of applications in this class, not in chapter 7, but since I'm doing my own notes now, this is going to be what I call Unit 3. But, if you take junior, senior level classes in engineering or math or stats or physics or chemistry, maybe not biology. I used to think biologists had to do a lot of math, and then since I started working here, I started looking at biology degree plans, from other universities even, just to compare and contrast curriculum here. And man, I'm surprised that biologists really don't have to take math, which is kind of weird because there's a lot of applications of math in biology, like even something as simple as just like studying an ecosystem. Populations of ecosystems are really described by differential equations. And so I don't know what universities are doing by only allowing their biologists to take like calculus 1, or in some cases not even take calculus 1. But these applications are all over the place. The reason we care about finding antiderivatives is because antiderivatives allow us to calculate integrals. Even though an integral is defined as the limit of a Riemann sum as the number of rectangles goes to infinity, you guys know from Cal 1 that an easier way to calculate integrals, faster a lot of times, is to take an antiderivative and then evaluate the antiderivative at the bounds of the integral. So this is what's called the fundamental theorem of calculus. The first part is relating antiderivatives, the capital F, to integrals of the original function. And then the second part is giving us a formula for calculating the value of an integral, which, like I said, is you find the antiderivative, you plug in the upper bound, you plug in the lower bound, and you subtract. I'm not going to give you a proof today because, in the interest of time, I'm going to include that proof in my Calculus 1 class instead of Calculus 2. And so if you're interested, you can go back on my Calculus 1 page and see that. But just as a little reminder, if I have an integral from 2 to 5 of x squared, we are going to say, okay, my original function is x squared. What's the antiderivative of x squared? 1/3 x cubed. Yeah, that's one we even talked about earlier. Potentially plus a constant, right? But what we're going to see is if you have a definite integral, one that has its bounds defined like this, then the constant's not going to matter. Because if I plug in my upper bound and I plug in my lower bound and I go ahead and subtract what I get here, what it will be is 1/3 5 cubed plus c minus 1/3 2 cubed plus c, and the c's are going to cancel. (125 minus 8 is 117. 117 over 3 is 39. So, yeah, I've got a positive plus c minus the same plus c, right? And so if I subtract c minus c, then it cancels out. And it turns out that constant doesn't matter. It doesn't matter what antiderivative you choose, because any kind of constant you add to it is going to cancel itself out. So the value of this integral is well defined, and it's exactly 39. Just like with derivatives, antiderivatives possess the properties of additivity and homogeneity. And so this is the property of additivity. Additivity means if I'm trying to take an antiderivative of a sum of two functions or a difference, right? This could be plus or minus. Well, then I can just take their antiderivatives separately and then add them together. That's super easy. Homogeneity is the next one. Homogeneity means if I have a constant multiple of a function and I want to take its antiderivative, well then the constant multiple just, it's along for the ride, right? It doesn't, nothing special happens to it. Just worry about the antiderivative of the function. And that's true of derivatives as well. The next thing that you might think about is what we call integral domain additivity. And the way it works is like this. I've got my y-axis and my x-axis. And here's a function. And I want to know what is the integral of this function between this point A and this point C. Well, if I wanted to, if there was some motivating reason why I would want to split this into two integrals, one integral from A to B and another integral from B to C, to get the original integral that goes all the way from A to C, I could just add those two together. So it's a way to partition the domain of the integral. But that rule always works for any function in your integrand, as long as these match up. Another one that I forgot to put in my notes that I should really go back and, for next time I teach this class, next year, I'll definitely include this, would be this. If I have an integral from A to B of a function, then this is the negative of the integral where I switch the bounds. I don't know what this property is called, but it means that switching the order of the upper bound and lower bound just gives a negative. And this is not so hard to prove on your own because, right, we're just taking an antiderivative and then subtracting. If you switch the bounds, you switch the order of subtraction, and that's kind of like multiplying by -1 on the whole thing. Do you guys have any questions so far? Just review. Okay. Next, the integral is equal to the signed area in the xy plane between the curve and the x-axis. And when I say signed area, I mean that area above the x-axis counts as positive area, while areas that are below the x-axis count as negative area when you get the net total. So the best way to see this is by example. We'll focus on these two. But if I want to know about the curve y equals cosine of x and the area between the curve cosine of x and the x-axis, well, here's my function cosine. What is this location on the x-axis right here, where the value of the function is 0? It's negative pi/2. And cosine is an even function. So it has reflection symmetry across the y-axis. What is this value of x? Pi over 2. So if I go ahead and I take the integral of cosine between negative pi over 2 and positive pi over 2, that should give me the area that's bounded between this curve and the x-axis. And since this area is above the x-axis, it should count as positive area. So let's see what happens. The antiderivative of cosine is sine. And I don't have to add plus c this time because I know it would just cancel out when I plug in the upper bound and I plug in the lower bound and I subtract the two. So I'm going to end up with sine of pi over 2 minus sine of negative pi over 2. What's sine of pi over 2? 1. What's sine of negative pi over 2? Cool. So the value of this integral is 2. In other words, that green area has an area of 2. In Desmos, you can check your answer. I think it's a really smart idea to always check your answer in Desmos. Like, here's my cosine of x function. And if I want an integral in Desmos, I type in int. Just the letters int automatically pops in the integral. And then if I want negative pi over 2 up to pi over 2, just plug in those bounds. And then say my function is cosine of x. Desmos can tell me the answer is 2. Cool. The next question right below it is asking again about the same function cosine x, but it wants to know what is the area from x equals negative pi over 2 up to x equals positive 3 pi over 2. The area between the curve and the x-axis. So we already said this was the point x equals negative pi over 2. What is this point right here? 3 pi over 2. So if what I said is true, then the areas above the x-axis are going to count toward my total as positive areas, like this one. But this time, I'm also including a little bit of area in between the x-axis and the curve here, where it's below the x-axis. And I said that this was going to count as negative area in my total whenever I take an integral. So let's see how that integral shapes out. We're going to have the integral from negative pi over 2 up to 3 pi over 2 of cosine x dx. And the antiderivative of cosine we said is sine. So whenever I plug in the upper bound and plug in the lower bound, I'm going to get sine of 3 pi over 2 minus sine of pi over 2. Negative pi over 2. And what is the sine of 3 pi over 2? Negative 1. And we already said that the sine of negative pi over 2 is negative 1. And so I'm going to have negative 1 minus negative 1, which is 0. And that makes sense, right? Because the positive area cancels out the negative area, and they just annihilate each other in the total. So if I wanted the total area between the x-axis and this curve, what I should really do is take this green area and maybe just double it and say that the total area has to be 4 because the red area is the same as the green area. And so the total area is actually 4 between the x-axis and the curve. We'll come back to this example if we've got time. I want to make sure I hit all the other topics like even and odd functions. We talked about this at length. Even function is a function for which f of negative x is equal to f of x. And an odd function is a function for which f of negative x is negative f of x. And this part is new. If an integral has a lower bound and upper bound that are equal but opposite, then if the integrand is an odd function, the value of the integral is 0. If the integral is an even function, the value of the integral is twice what you obtain by changing the lower bound to 0. So I'll give you some examples. Evaluate the following integrals while exploiting this shortcut for any even or odd integrands. So is this integrand even or odd? It's even. Yeah, x squared is an even function. So according to this rule, the second bullet point right here, I should be able to change the lower bound of this integral to 0 and double it, or multiply by 2. So we've already done this antiderivative a few times. This is going to be 1/3 x cubed. So it's going to be 2 times 9 minus 0. When I plug in the upper bound and I plug in the lower bound and I subtract, I get 9 minus 0. So it should be 18. So what's the reason for this? Why do we know this always, always, always has to work? Well, if I have an integral like this, where I've got some negative lower bound and some positive upper bound, let's say, and this is an even function. We'll call it e for even. It's an even function of x. Well, I'm going to take the antiderivative, and when I take the antiderivative, it's going to change that even function into an odd function. And we can set c equal to 0 because it doesn't matter what the c is, right? So I can change the even function to an odd function by taking its antiderivative. And so I'm going to take the antiderivative, plug in the upper bound, and then subtract what I get when I take the antiderivative and plug in the lower bound. And what it means to be an odd function is that when I plug in a negative argument like negative a here, it's the same thing as flipping the plus or minus sign on the overall function. That's just a property of odd functions. And so I get 2 times what I would get if I just plug in the upper bound. Alternatively, what if I go ahead and I have the same even function in the integrand, but I set the lower bound to 0? Well, then I have an odd function evaluated at the upper bound, minus an odd function evaluated at 0, but an odd function has that rotational symmetry about the origin. And so an odd function evaluated at 0 is always 0, right? Odd functions don't have a constant term. And so whenever I go ahead and I multiply this whole thing by 2, I get the same thing. So this rule is going to work for any even function in the integrand when your bounds are equal and opposite. Does that make sense? Okay. The next rule, or the first bullet point here, is even more helpful, because you don't have to do any work at all. You just know that if your integrand is an odd function and your lower bound and upper bound are equal but opposite, then the value of the integral is going to be 0. So here's an example. I see arctangent. I know tangent's an odd function because its tangent is sine divided by cosine, right? It's odd divided by even, so it's going to be an odd function. Tangent's an odd function. The inverse of any odd function is an odd function. That's a rule you can keep in your back pocket. So arctangent is also an odd function. And if I've got this integral of an odd function and the bounds are clearly equal and opposite, it's just going to be 0. Ta-da! No work required at all. And the reason this has to work, the reason this will always, always work, is because if I have an odd function, I'm going to take its antiderivative, and I'm always going to end up with an even function when I take the antiderivative. So I take the antiderivative and I plug in the upper bound, and I subtract what I get if I plug in the lower bound. What it means to be an even function, though, is if I plug in negative a, it's exactly the same as if I were to plug in positive a. And so I've got my even function evaluated at a minus my even function evaluated at a. That's 0. And the only real, requirement here is that the integrand is odd and the bounds are equal and opposite. So do these rules make sense? A little bit. Okay. Here's another one. Might require a little bit more thinking. But when I look at this, I think, okay, bounds are equal and opposite, so there must be some kind of even-odd rule going on here. This part is an even polynomial because it only has even powers of x, and even polynomials are allowed to have constant terms. So that's even. Cosecant x raised to the 5th power is the same thing as 1 divided by, what's cosecant? Cosecant's the reciprocal of
Cosine.
Oh, it's just the reciprocal of sine, actually. Yeah, I know the cos are flipped on the reciprocal trig function, so it's confusing, but cosecant is actually the reciprocal of sine, so I've got 1 over sine to the 5th power. Sine is odd. Everybody should always remember that sine is odd. The number 1 is even, and when I have even divided by odd, that's going to give me odd. Because multiplying or dividing functions, if I've got even and odd that I'm multiplying, it's going to give me odd. If you can't remember how multiplying functions works, I just think like something like this. That's even times odd, and it's odd. Or if I really wanted to think about even divided by odd, that's odd, right? You can come up with little toy examples, right, that are easier to think about even divided by odd being odd. So cosecant is odd. And so what I have here then is like cosecant x, an odd function composed with something to the 5th power. In other words, I have an odd function composed with an odd function. I've got a little odd function composition. And again, if I don't remember off the top of my head how this works, I could think to myself, what does it look like when I have an odd function composed with an odd function? That would always give me another odd function. So odd composed with odd is always odd. Okay, so back to my integrand. I've got an even function times an odd function. What's an even function times an odd function? Yeah, even times odd is odd. And so I've got a negative lower bound that's opposite but equal to my upper bound, and the integrand is odd. So what's the value of this integral?
0.
0. Okay, let's go over some U substitution next. Like, I just told you this is going to be a U substitution problem, so what should be my little lowercase u I'm going to apply here?
X squared.
X squared. Very good. And that means the derivative of u with respect to x is
2x.
2x. And that means if I see something like 2x dx, I could replace it with du. And that means, let's go ahead and rewrite this as cosine of u du. I replaced the x squared with a u, and I replaced the 2x dx with a du. So Gwen, I know what Kyle did in Calculus 1, because he took Calculus 1 from me, but did you do this in Calculus 1? Okay, very good. So you find the antiderivative. It's sine, don't forget the plus c, and then we just reverse the substitution, and we get sine of x squared plus c. Perfect. So in this sense, we can use U substitution to reverse the derivative chain rule. If I was going to take this derivative of sine x squared, it would require the derivative chain rule. And there's some sense in which this type of U substitution works especially well when the integrand looks like a derivative somebody found with the derivative chain rule, right? And for that reason, if I'm doing a U substitution, the first thing I might try is like something inside another function. So I'm sure what Kyle was thinking of is like, that's a cosine of x squared. X squared's on the inside, so let's try that for our U first. That's a good place to start. This is a little bit more subtle. In this example where I've got tangent times natural log of cosine, that advice doesn't always work, because here I'm thinking this is the thing inside, right? I'm taking natural log of cosine. And so what would it look like if I follow my own advice and I say u is equal to cosine? Well, the derivative of u with respect to x would be negative sine of x. And so the thing I would try is like, let me look for a place where I've got negative sine of x dx. And then replace it with du. Maybe this does work. Let me try it out. Let me see if it's gonna pan out. Because tangent is the same thing as sine over cosine. So this might actually work, but we'll see. I can replace the sine of x dx with negative du. And then the cosines we can replace with u's. Now I'm stuck with this kind of antiderivative of u to the negative 1 power natural log of u. Okay, well, that's something you might be able to do with a strategy called integration by parts. And we will learn about integration by parts next week, I think. If not the week after or the week after. We're going to eventually learn integration by parts. But I don't see right now with the strategies we know today how we would do that. So if you're trying to solve an antiderivative with u sub, sometimes you don't guess the correct u immediately, right? Sometimes it doesn't work. So what do you do when it doesn't work? You get out your eraser, you erase everything, and you try again. Just like Daniel Tiger says, keep trying, you'll get better. All right, here's my next guess. Let's say that u is equal to natural log of cosine x. What's the derivative of this? Nice. So it's the chain rule. The derivative of natural log is 1 over blank. And then we multiply by the derivative of cosine, which is negative sine. Very good. We said this a second ago. Sine divided by cosine is tangent. So I could replace my tangent x dx with negative du. And then I take the antiderivative. Give me 1/2 u squared. Oh yeah, and this is just an antiderivative. This is not a integral. And then I replace, I switch, what do you call it? I reverse my little substitution here and I call it negative 1/2 natural log of cosine x squared plus a constant. Antiderivatives are really difficult, right? In calculus 2, we find a lot of antiderivatives, and it's really tough. It's harder than finding derivatives. But the good news is that you can always check your work after you find an antiderivative by just taking the derivative of your answer. And so if you were taking a test, you don't want to lose any points, you're not 100% sure of this answer, you could just take the derivative again, make sure that you get tangent of x times natural log of cosine of x. Yeah, it's a little bit more subtle for a u substitution. I've got two more to show you that I want to get to in the next 6 minutes. So really quick, what would I use as the u in this u substitution?
X plus 1.
X plus 1. So the tricky thing about this is that there's nothing special about swapping the dx with the du, but after I replace the x plus 1 with a u, what do I do to get rid of the x?
Would you
That x.
solve for x, like at that top one? Yeah.
And write x equals?
Negative u plus 1?
No.
Oh wait, no.
Yeah, just subtract 1 from both sides. But yeah, you got the right idea, okay, Kyle. Is this x is going to become u minus 1. And then I'm not going to finish solving this entire thing for you, but what you should realize is that this is the same thing as u to the 3/2 power minus u to the 1/2 power. And with the antiderivative additivity rule, I can break this up into two separate antiderivatives and think about it that way, and that's your path forward. Because u times square root of u is u to the 1.5 power, and square root of u is u to the 0.5 power. Okay? I trust that you can figure it out from there. We also did this exact problem in Calculus 1. So like I said, this is kind of a review. This is one that we did not do in Calculus 1. And this is the trickiest one of all. This is the most hidden of the substitutions. The hardest one to figure out on your own, I think. It's really quite a riddle. But there's a little bit of algebra we can do to this thing to make it possible to use a u substitution. I'll just show you how this example goes. I'm going to multiply the integrand by 3. And I'm going to put a little 1/3 in front to balance that out. And that way I get a 3 in my numerator. The next thing I'm going to do is in the numerator, I'm going to add e to the x. And to balance that out, I'm going to subtract e to the x. And then I can separate this fraction right here at the minus sign. And what I would get for the first fraction is 3 plus e to the x divided by 3 plus e to the x, which is 1. And for the next fraction, what I would get is e to the x divided by 3 plus e to the x. This is finally the point where we can reveal what the u substitution has to be. And in fact, even before doing a u substitution, you would also think about separating this a little bit, right? Antiderivative additivity at work here. And don't forget the 1/3 applies to the whole thing. But for the second antiderivative, my u substitution is going to be 3 plus e to the x. And that way the derivative of u with respect to x is e to the x. And I can replace e to the x dx with du. So in the first place, I've got antiderivative of 1, which is x, and so I'll have 1/3 x. In the second place, I've got, again, the 1/3 that distributes. Antiderivative of 1 over u du. The antiderivative of 1 over u is the natural log of u. And so I'm going to replace the u with 3 plus e to the x. And don't forget the plus c. But that is like the trickiest kind of question I could ask. The trick or the strategy that you would have to think about going into this is like, well, first of all, I just don't know any antiderivatives of this big, ugly integrand. How could I make the numerator look like the denominator? Well, I would want the constant to be a 3 and not a 1. So multiplying by 3 does the trick. And then if I just multiply by 3, the next thing I need to do is add e to the x. So I add e to the x. How do I balance that out? I also have to subtract e to the x. That's kind of the strategy.